So we left off last week with our unit test, and hopefully you've all got that turned in. I haven't. I've been avoiding logging in over the weekend here, over the holiday. I will be looking at those this afternoon and hopefully getting either this afternoon or tomorrow morning, getting them all graded and posted for you, so that your grades will be updated there. Like I said, if you haven't got those turned in, please do so as soon as possible so we can get everybody's grade updated. Without those in, makes your grade look a little poor at this point. So now for this next unit here, we're going to look at applications of this trig in ways that are going to be very specific for construction needs. To do that, however, we need a couple of basic strategies. So we're going to be using trig and other strategies to find areas. So the first thing we're going to look at here is triangles. Our basic formula for finding the area of a triangle was if we had a generic triangle with no right angles in it. We had a base and we had a height, height that went from the opposite vertex, the one that's not connected to our base, to that base at a right angle. Sorry about that. Seasonal allergies are coming in with a vengeance this spring. So anyway, the area of that triangle is the base times the height divided by 2. Or some of you may have learned the formula is 1/2 base times height. Comes out to the same result. Well, if I have a triangle let's say I know that the base is 28 inches. But instead of having the height, I know that this side over here is 13 inches. And I know that this angle right here is 68 degrees. I would argue that what I have is a base and a height. So this is the base. The height would be right here. Well, you'll notice that when I draw in that height, it forms a right triangle over here. And I have the right angle, but I also have this angle and the 13 inches, which means I can find that height. According to my 68-degree angle, the height would be my opposite side, and the 13 would be the hypotenuse. That's going to be dealing with sine. Sine theta equals opposite over hypotenuse. So in this case, the sine of 68 degrees equals that height over 13 inches. And I'll put this over 1 so that I can cross, multiply, and divide. Sine of 68 times 13 divided by 1. Giving us 12.05 inches. So the height is 12.05 inches for that. So now I could find the area as 28 inches times 12.05 inches divided by 2. Here's 168.75 square inches, or inches squared. Well, if we look at what just happened there, and instead of giving you the base and the side over here, I'm going to say that I know this angle. I'm going to call that angle theta. I'm going to call the base side A, and this side over here side B. In fact, rather than calling that angle theta, let's call that angle C. So this would be angle A, angle B, and side C. If I know sides A and B and angle C, Now you might remember this from last unit as being two sides in the included angle, which is what we used for our law of cosines to find the other side. But here we're looking for the area of the triangle. The area of the triangle is going to be the base, A, times the height. Well, the height is B times the sine of angle C. That would be the height. So base times height divided by 2. So the area of a triangle can be found by having the length of two sides and the size of the angle, or the sine of the angle that's between them. So let's say I'm given that this angle here is 31 degrees. This side down here is 26 inches, and this side up here is 21 inches. The area, again, I have two sides and the included angle, or the angle between them. My area will be 26 times 21 times the sine of that angle, 31 degrees, divided by 2. Here's 140.61 square inches is the area of that triangle. Now, of course, it does not stay quite this simple. We can be given other combinations of sides and angles. Might be told that this angle here is 81 degrees, and that this side here is 52 inches, and this side down here is 63 inches. Here, we do not have a side, or the two sides and the angle between them, or the two sides and the included angle. I would need this angle for that to be true. But I do have a side and its opposite angle, which means I can apply law of sines to this figure. So I've got the 63 inches over the sine of 81 degrees. That has to be equal to, now I'm going to label my angles here. I'm just going to go around ABC, so this will be side little a, little b, little c. It's going to be the 52 inches over the sine of angle C over here. So I can cross multiply and divide. Sine of 81 times 52 divided by 63. Give me 81.52, or 0.8152. So that angle C is the inverse sine of that. Giving me that C is, sine, second answer, 54.61 degrees. Now we always have to stop and ask a question of, are we sure, whenever we do that inverse sine to find the angle, we have to ask, are we sure that this is an acute angle? And yes, we are. This side is bigger than that side, which means this angle has to be bigger than that angle. So we know that that has to be smaller than 81 degrees. It has to be an acute angle. So we know the 54.61 degrees is reasonable for that answer. Now we know angle A, because we're going to subtract from 180. 180 minus the 81 and then minus the 54.61 is going to give us 44.39 degrees. Now we have two sides and the included angle. So now we can find the area as 63 inches times 52 inches times the sine of that included angle, so sine of 44.39 degrees, divided by 2. So 1145.84. That is inches squared. We might have a situation like this. Maybe my triangle ABC, little a, little b, little c, where we might be told that side C up here is 68 feet. Angle A is 51 degrees, and angle C here is 63 degrees. Well, at this point, again, we do not have two sides in the angle between them. But we can find, first of all, we can find the third angle here. We can find this angle up here rather quickly by subtracting from 180. 63 plus 51 makes 114. 180 minus 114 gives us 66 degrees. So this is a 66 degree angle up here. Well, that still does not give us two sides in the angle between them. We have all three angles, but we only have one side. We have to have a second side. So we are going to still, again, have to go back to our law of sines. We have the 68 feet over the sine of 63 degrees. Equals, and it really doesn't matter which side we find, but I'm going to find the side that's across from the angle that was given. So I'm going to do side A over the sine of 51 degrees. And we will cross multiply and divide here to find our missing side. So 68 times the sine of 51 divided by the sine of 63. 59.31 is what that length becomes. So this is 59.31 feet. And now we can find our area. That area, 68 feet times 59.31 feet times the sine of 66 degrees divided by 2. 68 times 59.31 times sine of 66 divided by 2 at 1842.20 square feet. So those are the situations we can run in with our triangles. Now, there is a fourth possibility. Like I said, here, the main possibility is having two sides and the angle between them. Very simple. That would be, what would normally be a law of cosines application is what we need to apply our area formula here, our trig area formula. Any other combination falls into one of two categories, where we either still have two sides but not the angle between them, and we use the law of sines to find those other angles, or we only have one side and two angles. And in this case, again, we use the law of sines to find the second side so we can apply the formula. The third possibility is having all three sides. Say I give you that side A here is 47 feet. Side C, I'm going to call it 59 feet. And side B, I'm going to call it 64 feet. So there's our sides. We can find the area using our Hero's formula from last semester. So let's start out by doing that. First step in Hero's formula is to find the perimeter. That'd be 47 plus 59 plus 64. Oh, what is that? 170 feet of a perimeter, I believe. Looks correct. Then we find our semi-perimeter, which is just our perimeter divided by 2. So 170 divided by 2 is 85 feet is our semi-perimeter. Then the area is the square root of that semi-perimeter, 85, times the semi-perimeter minus the shortest side, the 47, times the semi-perimeter minus the next side, the 59, times the semi-perimeter minus the longest side, which is the 64. That's going to be second square root, 85 times 85 minus 47 is 38, times 85 minus 59 is 26, times 85 minus 64 is 21, giving us 1327, 1328 really is what it comes out to be, square feet. The other way we could do this, using what we've learned this semester, if you don't remember Hero's formula, which I hope you do because it is a handy little formula, but we could find a missing angle here. We'll find angle C. We'll choose that to be the angle we find. And remember we said that C squared minus A squared minus B squared divided by negative 2 times A times B is equal to the cosine of angle C. This is a variation of that law of cosines formula. So we'll have 59 squared minus 47 squared minus 64 squared over negative 2 times 47 times 64 equals the cosine of angle C. So I'm going to do the top first here. 59 squared minus 47 squared minus 64 squared. And of course, that should give us a negative number. So negative 2824 over negative 2 times 47 times 64 gives us negative 6016. That equals the cosine of C. So C is the inverse cosine of that ratio, negative 2824 over negative 6016. Second cosine. You'll notice I'm leaving the negatives out, but I know that a negative divided by a negative is a positive. Whoops, say cosine, not inverse cosine. Second cosine, 2824 divided by 6016. There we go, we get 62 degrees for C. And go back up here, put 62 degrees in here, and I could alternatively find that area by doing 47 times 64 times the sine of 62 over 2. Give us 1,327.95 square feet. You'll notice that is basically the same answer. It's off by a couple of hundredths as we had before. It's just round off differences is all that is. So we get the same answer either way. Now, personally, I think Hero's formula is still simpler, so using the trig stuff is not terribly useful for this example. But if for some reason you've forgotten Hero's formula and happen to remember both this alternative law of cosines and our area formula, you can find the area in that way. So now, rather than to continue to harp on those examples, I want to move on then to the next type of problem we're going to do. Next type of problem involves finding the area of irregular figures, irregular shapes. This is actually an old surveyor's formula for finding the area of plots of land that are not shaped regularly. And it involves using a coordinate system. So let's say that we establish a 0, 0 coordinate and we establish an x-axis and a y-axis. Maybe we're using roads or whatever. And we have one corner of this piece of this shape. I'm going to use small numbers, not big numbers. The numbers I'm going to use are going to be chains. One chain, remember, is 66 feet. So let's say that this first corner of the property is 4 chains. Now, four chains is 264 feet to the right in the X direction, and 2 chains, or 132 feet in the vertical direction, the Y direction. There's a second corner of the property over here. It's going to be 15 chains in the X direction and 4 chains in the Y direction. Another corner up here is going to be 13 chains and 13 chains. And then a final corner right here, which is going to be 3 chains and let's go 10 chains. Make it fairly simple. So we have this shape. It's a 4-sided shape, not necessarily a rectangle. We could use our distance formula from last semester to find the distance between those points. Really doesn't do us a whole lot of good here because we don't know if we have any right angles or not. We could use slope formula to find out if we have right angles and prove that we don't. But I'll tell you right now that those corners are not right angles. The way we find the area of this using the surveyor's formula, it's actually a simplification of a more complex formula that uses matrices like we did at the end of last semester when we were doing those systems of equations. We did Cramer's rule using the determinants of matrices. We could actually use the determinants of matrices to find the area of this shape. But we're going to simplify it and take the matrices out of it because it's a little tricky to create the matrices needed. So what we're going to do is we're going to pick a starting point right there. Change colors here so it's not. So that's step 1, is pick a starting point. So I'm going to write that down. My starting point here is 4, 2. Step 2 is to move around the shape counterclockwise. Counterclockwise would be this direction. So our next point would be this one here, the 15, 4. Next one's this one here, 13, 13. Then we hit the 310. And it's called closing the loop. We have to close the loop to get back to where we started. So that would take us back to 4, 2 here. If we don't close the loop, we won't get a closed area or closed shape. So we have to repeat whatever point we started at is what we have to end with. Now we do diagonal products. So we're going to go 2 directions. The first one, we're going to start with the coordinate on the right, and we're going to go down into the coordinate on the left, and we're going to go down into the right. We're going to start with this 4, and we're going to times that 4. So 4 times 4 is 16. 15 times 13, what is that, 195, I believe. It is. 13 times 10 is 130, and 3 times 2 is 6. And we are going to add those up. Find the sum. So if I find the sum of that, 16 plus 195, that's 211. 341, 347 is my total, my sum of those diagonal products. But now I need to do the diagonal products in the other direction. I'm going to start on the right and work my way down into the left. So 2 times 15 is 30. 4 times 13 is 52. 13 times 3 is 39. And 4 times 10 is 40. I need to add those up. What do I have there? I got 91, 70, 161 is what I get there for my total. I need to find the difference between those totals. And then I'll divide by 2. So I have 347 and 161. The difference will be the larger minus the smaller, 347 minus 161, which is going to be 186. I'll then divide that by 2. 186 divided by 2 is 93. The 93 square chains is the area of that. Now, the reason I used square chains is 10 square chains is an acre. So 93 square chains is 9.3 acres is the size of that piece of property. Now, I could use any unit. I could have used feet. I could have used yards, rods, whatever. For this first example, I wanted to keep the numbers small so that we could do it rather quickly and easily. You didn't have to deal with some huge numbers. If I did it in feet, we would have some huge numbers. You'd have a couple hundred for each of those for many of those numbers, and it'd get to be really huge multiplications. Now, to prove to you that this method works, let's look at a right triangle. So I'm going to say that this vertex of this right triangle is at 5, 2. This vertex here is at 17, 2. And this vertex up here is at 5, 13. Just by subtracting coordinates, we can find that this is 12 units in size. That's the difference between the 17 and the 5. Remember, the x-coordinate describes the horizontal distance. And this here is 11 units. That's just the difference between the 13 and the 2. So the area would be 11 times 12 divided by 2, or 66 square units. Whatever the units are on that graph. But let's use our coordinate method to find that area. So I'm going to start with 5, 2. Then we go to 17, 2. Then 5, 13. Then back to 5, 2. Then we'll do our diagonals. Here we've got 5 times 2 is 10. 17 times 13. It's morning, 221. And 5 times 2 is 10. That adds up to be 241. Going the other direction, we've got 2 times 17 is 34. 2 times 5 is 10. And 13 times 5 is 65. Adds up to 109. So now again, we take the bigger one minus the littler one. So 241 minus 109, which is going to give us 132. Divide that by 2, it is 66 units squared. So we get the same answer using this coordinate formula. Now the nice thing about the coordinate formula is we don't have to have all positive coordinates. And we don't have to have, we're not limited to just 3 or 4 vertices. Let's put a vertex here at a -4, -3. Put a vertex here at 4, 2. Put another one here at 12, -4. We're going to put another one here at 9, 7. We're going to put one here at -7, 8. And let's just connect that off for now. So we need to pick a vertex to start at. Really does not matter which one. I'm going to pick the 4, 2. Going around counterclockwise, then we have the 12, -4. The 9, 7. -7, 8. the -4, -3, and then back to the 4, 2. Very important that we repeat that first point again at the end. Now we've got 4 times -4 is a -16. 12 times 7 is 84. 9 times 8 is 72. -7 times -3 is a positive 21. -4 times 2 is -8. So we have to add those all up. Gives us, I believe, 153. Looks good to me. Let's go the other direction now. So here we got 2 times 12 is 24. -4 times 9 is going to be a -36. 7 times -7 is a -49. 8 times -4 is a -32. And -3 times 4 is a -12. So when I add this up, I'm going to get a negative number here. I get a -105. So it is still the larger minus the smaller. 153 minus a -105. Now remember, minus a negative is the same as adding a positive, so this is just 258. And we'll divide by 2, get 129 square units. So whatever the units are for the grid points on the graph, that is our units. Square units would be our area. Now we don't even need to have the graph shown out for us. We just need to know that we have the coordinates going counterclockwise around the object. If I give you that we have the coordinates here, 7, -2, 12, 5, 6, 11, -3, 8, -5, -4, and let's go -1, 1. To find the area of that, I start with my first point here, trusting that it really is going around counterclockwise. I'm just going to list them. 7, -2, 12, 5, 6, 11, -3, 8, -5, -4, and -1, 1. Now there's something I'm still missing here. Remember, we always have to list the first point again at the end. We have to get back to that starting point. So we got to list that 7, -2 again. And let's do our diagonal products. We have 7 times 5 is 35. 12 times 11 is 132. 6 times 8 is 48. -3 times -4 is 12. -5 times 1 is -5. And -1 times -2 is a positive 2. So if I add those together, we have I believe that's 224. Going the other direction, we've got a -2 times 12 is a -24. 5 times 6 is 30. 11 times -3 is a -33. 8 times -5 is a -40. -4 times -1 is a positive 4. And 1 times 7 is 7. So what do I have there? Because I have a -56. So again, I'm going to do the larger minus the smaller. So 224 minus a -56. Well, again, minus a negative is the same as plus a positive. So that ends up being 280. Dividing that by 2 is relatively simple. It gives us 140 square units is our area. Okay, so at this point in the course, like I said, I want to make sure I give you all plenty of work time. And when we're in the classroom, generally time to work in a group, especially on quizzes and stuff. For right now, your homework is there are 2 worksheets attached to a Blackboard for today, for April 6th. One of those worksheets goes over that first formula. The area of the triangle is A times B times the sine of C over 2. And the second worksheet is this surveyor's formula for finding area from the corner coordinates of a section that we just went over. So I will give you guys the second hour of the class to work on that homework. I'll be on the network here for a while for you. If you have any questions,